Okay, so we are going to use our model to take a look at a lasagna heating on the counter. So take a moment to read this over, and then we'll take a look at finding some values for our parameters. Alrighty, so we're taking a look at this. Our sort of baseline differential equation is ds dt equals negative k times S minus our room temperature of 70 degrees. And we have an initial temperature of 38. Now we know, in this case, we know what our solution, the format of our solution, so is going to be. We have that S is equal to T naught plus C, plus C over e to the kt. Okay. Where in our case, T naught is equal to 70. So this is that temperature that we're going to be approaching. And our job is to find values for the constant C and the constant K, just telling us how quickly we're heating. Okay, so we're given some initial information. So we are told this initial condition that at time 0, our temperature was 38 degrees Fahrenheit. So we're going to use this to find out the value for capital C. Indeed, we have that 38 is equal to 70 plus C over e to the k times 0. Or 70 plus, solving for C, we get that C is equal to 38 minus 70. Which is negative 32. Negative 32. Yep. Okay, so we're making good progress. We find that S is equal to 70 plus negative 32 over e to the kt. And we can look for this value of K by looking at the second temperature that was given to us. So it says that half an hour later, we've warmed to a temperature of 45 degrees Fahrenheit. Okay, so if we're looking at our temperature in terms of hours, we know that S of 0.5 is equal to 45. And so we can put these values into our equation. We get 45 is 70 plus negative 32 over e to the k over 2. And then we're just going to do a little bit of algebra to solve. So 45 minus 70 gives us negative 25 equals negative 32 over e to the k over 2. Okay, we can take the reciprocal of both sides, and that gives us that negative 1 over 25 is e to the k over 2 divided by negative 32. We can drop these negatives because we've got a negative on both sides and solve for our exponential. 32 over 25 is e to the k over 2. And we could undo this exponential by taking the logarithm of its sides. So natural log of 32 over 25 is equal to k over 2. And so we have 2 natural log of 32 over 25 equals k. Now we'll put this into a calculator to find an approximation for this. And we find a K value that's equal to 0.494. Okay. All right, and so this tells us S of t is equal to 70 plus negative 32 over e to the 0.494. Okay, so here is our model. And if we take a look at this, we see that over time, it's approaching that final temperature of 70 degrees Fahrenheit. We see that our values are going to be increasing up to 70. And our question was, how long does it take us to warm to 60 degrees Fahrenheit? So the temperature that we're looking for is 60 degrees. And we're just going to solve for time in this situation. So let's take a look. We have 60 is equal to 70 minus 32 over e to the 0.4914. We're just going to solve for this time. Okay. Alrighty, and we can simplify this as we're going. Okay, take reciprocals of both sides. Right, we get 16 fifths is e to the 0.494t. Take the logarithm of both sides, and we have 0.494t. And then solve for t. So log of 16 over 5 divided by 0.494. And we should keep in mind what our units are going to be here. So we built this using hours. Okay, so the units of this answer are going to be in hours. And so here we see that it's going to take, according to this, 2.35 hours to heat up to 60 degrees. Okay, we should make sure that that kind of matches what we might expect. Okay. One place that that we sometimes run into problems here is if we have incorrect units, for example. We might get an answer and think, wow, that's way too big. And you really want to train yourself to think, like, does this answer kind of match the information I have about the problem, and does this match kind of my experience? Okay. Alrighty. Next, we're going to look at a further we're going to look at a more detailed version of this model.